Ahead and start by actually checking my phone. I just want to make sure we don't have any audio artifacts going before we start. How's everybody doing this evening? You guys, who's all taking the test tomorrow? So, turns out there's a couple testing dates. Um, that's not the right thing. Hang on. Found out it's actually rather difficult to talk and try to operate things on my phone at the same time. Yeah, so we are here today because the first AP test, okay, yeah, it's live. Because the first AP test date is tomorrow for AP Physics 1. And so we're going to conclude our 8-part review series that we've done with a cumulative review. We're going to be taking a look at all of the topics that are going to show up on this test just in a broad scope. We're not going to delve too much into the problem solving and practice problems. If you want to do practice problems, you can just check out some of our older streams. They're going to be archived on 314 Education, and you can probably find them somewhere on YouTube and Twitch as well. And so, with that being said, let's go ahead and get started. And so, we're just going to begin by looking at the exam in just generally like what we can expect for format. Now, there's 7 topics or 7 units that show up on the exam. That's these guys here. We have our kinematics, dynamics, centripetal and gravitation, so centripetal motion, work, power, and energy, momentum and impulse, simple harmonic motion, and torque and rotational motion. Now, each one of these topics has its own individual review episode that we did. If you want specific review for problems on that unit, you can go back and check those out. But we'll be talking about the big ideas of each unit and what kind of things we, like the big takeaways to remember for each, for different approaches, really. That's kind of what we want to focus more on this time is how we approach problems. Because one thing that is going to be kind of new for different to compared to what we've studied is you won't know what unit the question that you are asked is testing from. And so this means that we'll have to be able to identify what strategies we want to use for each problem, and then what kind of indicators let us know which techniques we want to use. And so, depending on which exam you're taking, the one tomorrow is going to be the in-person or the paper exam. Both will begin with a multiple choice section. The section 1 multiple choice up here, we see we've got 50 questions for both cases, and you get 90 minutes for that. So that's going to average about a little less than 2 minutes a question. And so you'll find that this average is really gonna kind of vary, right? Because some problems you'll be able to fly through very quickly, and some might take a little bit more time. You'll have to write out some calculations. You are not obliged to show work on the multiple choice section, but you will have access to as much scratch paper as you want, so feel free to. You won't get any bonus points for showing work. So if you are able to do something quickly in your head, you might as well, but just be careful because there will be trick questions which seem easy, but then there's actually a little bit more nuance to it. And then for the second section, this is where the paper exam differs from the digital exam. This is the free response section. And so for the in-person exam, this is all free response. You will have 5 FRQ type questions, one of which will be the experimental design problem, where you'll have to come up with a procedure to solve for a specific variable using some sort of physical experiment. And typically, the thing that you'll be asked to solve for won't be something you can measure directly. It'll be something that you can deduce from other things you'll be able to measure directly. And then you'll have to do a little bit of mathematics to kind of rearrange your data to get the answer that you're looking for. We have qualitative, quantitative translation. So that's going to be sort of the standard FRQ type of thing we've seen. You might even be working with data. So they give you information about a theoretical experiment they've seen, and then they'd ask you to interpret that data and to ask what that means about different things that were tested in that hypothetical. And then we have short answer. Notice how this is paragraph arguments. So this is like a written part, but this also is not an English test. So paragraph, try to express all of your ideas as well as you can, but they're not going to dock you points for a run-on sentence or for, I don't know, for, I guess, the English of it. But you do want to make sure you're able to communicate your ideas clearly. So it does help to try to keep things neat. Also, by the way, I didn't mention earlier, but on to the left here, if you see me looking over this way, I have chat windows available from Twitch, YouTube, and 314 Education. Should all be funneling to this screen here. So if you see me looking over here, this is me just checking the chat window. If you have any questions, I kind of hope this can be a bit of a helpful. I want this to be helpful for you guys, and so I was hoping this could be kind of a Q&A if you guys have any specific questions about how we're deriving some of these equations or what we might expect to see for certain types of problems. If you have any questions, just throw them up in the chat, and I will be checking these periodically, and I'll try to answer them all as best as I can. Yeah, and so before the digital exam, this section 2 is now cut with multiple choice section as well as free response. So instead of 5 free response questions, you're only having 2, but you have an additional 25 multiple choice questions. So if you prefer multiple choice over the written response questions, maybe the digital exam is the version for you. If you prefer doing the FRQs over multiple choice, then perhaps the paper exam is the version for you. And so I found out literally today, there's actually a second testing date for the in-person exam. I believe that is May 24th. So some schools might be taking it at a later date, although I think the majority will be taking it on the 5th, which is tomorrow. And so, yeah, with that being said, let's start taking a look at our units. And so what I figured we'd do for this is we just take a look at each unit individually and try to write out all the important relations that we used in this unit, the kind of major ideas, and just see how they link together. And then what kind of things that might be a good question could be asked of this unit. So we'll begin with kinematics. And so kinematics fundamentally is the relationship between position, between velocity, and acceleration. And so these things are going to be linked because these describe motion, but each of these 3 ideas denotes the rate of change of something, except for position, I suppose. Position is just kind of where we are in space. You define a position in some coordinate system, and that's where you are at that time. Now, velocity is going to be the rate at which your position changes with time. And so notice how velocity is going to be related to position or displacement. So these are what we call vector quantities. And something like speed would just measure the distance change over time. This is what we call a scalar quantity. Now, the really key difference would be scalar quantities do not imply a direction. A vector quantity, we need to include a direction with it. If not, then we're really just expressing the magnitude of that vector. I think there was that Despicable Me, where there was the villain that was Vector, who had both direction and magnitude. That's really what you need to remember for vector quantities, is they do have both a magnitude and a direction. Now, so for this case, with a vector quantity, you can usually break them apart into a triangle, into components in an x direction and a y direction. And then eventually we'll get them into a z direction, but we won't be dealing with that on tomorrow's exam. And so all you do to break something into components is you take your main vector, which would be the hypotenuse here, and you just follow from the tail of the vector going up to the tip of the vector. You travel only along directions on your coordinate system. What is the magnitude of my vector? Well, I don't know. If your vector is the hypotenuse of this triangle, I can find that magnitude by using Pythagorean theorem. So Pythagorean theorem tells us that a squared plus b squared equals c squared. And in this case, that would usually be our x component plus our y component is going to equal our resultant component, or our hypotenuse, whichever term you prefer. And then also, as usual, we'll be able to use, because these will be right triangles, because we expect our components to be perpendicular, we'll be able to find our inside angles here and then use all of our trigonometry relations with these. So if we have information about one side, but we have information about the angle also, we can find the other two sides using sine, cosine, and tangent. You're welcome, Morty. Um, wow, I felt like Rick there, for better or for worse. So let's start taking a look at some of these kinematic relations here. And so typically we think of, so if we have distance is going to be our x final minus our x initial. That is going to be the rate of, the distance is going to change with velocity. So that would be our average velocity times time. And we can really just call this quantity distance, or displacement if we're keeping the signs the right way around. And if we have an average velocity, we can write that as v final minus v initial over the time we move between them. And then, wait, oh yeah, no, that's right, there we go. And then we can multiply this by t, and then that gives us our distance here. Although, hang on, I feel like I screwed that up there, because that velocity times time, change in velocity over time. Oh, sorry. Yep, I did screw that up. This isn't over time. We're finding the average. Vf minus Vi, that's acceleration that I just did. So yeah, good thing so a good way to check these is checking the units. That's how I caught that something was off there, because we got units of velocity on the end there, even though we wanted units of distance. And so we wanted an average. The average isn't final minus initial, that's the change. Average is going to be final plus initial divided by 2. There we go. That's the expression that will show up on the equation sheet. So we should deal with rates of change, and so that would be the rate of change, let's say, of velocity. Well, the rate of change of velocity is acceleration, but we can define the rate of change as the final minus the initial over the time it took us to get there. And so that gives us A equals Vf minus Vi over t. But we'll also see this equation written out, rearranged for V final, where if we have V final, we have to multiply both sides by t to bring this t over here. And then we want to bring this Vi over to the other side also, giving us that our V final is going to equal our V initial plus our acceleration times time. The velocity we end with is the velocity we started with by the amount that we changed our velocity for the amount multiplied by the amount of time we did that change for. It's a good strategy to try, look, and find what equation will give the units you want. Absolutely. Don't know how to solve the question. Yeah, it's a good approach. Typically there'll be kind of certain like signals that we can look for that will like kind of indicate which way we want to go. But if you are really struggling to work out what the equation is, you can usually get away by using the looking for the, what's the word I'm looking for? The units, excuse me. Looking for the units, and by rearranging things, you'll be able to get an idea. Now, the only problem with this approach is it doesn't account for unitless scalars. So an example of this would be something like, say I wanted to find spring potential, and I went with units, I know I'm looking for newtons times meters, so I could take my K value, which is newtons per meter, and then multiply it by meters, and then multiply it by meters again. And then I get this idea that my spring potential is going to equal kx squared, and that doesn't actually account for the 1/2 because the 1/2 is unitless. But that's a good idea to kind of get us in the right area to think, oh, well, I'm looking for an equation that's going to have this sort of a form. And then if we can, if maybe that helps guide you towards the equation, because hopefully, I mean, ideally, there won't be any questions on tomorrow's exam that will use any equations that you haven't seen before. The tricky part is identifying them. That's the real challenge here. I'm gonna take this off here. We'll take another look at spring potential once we get to work, power, energy. But let's just finish off these last couple kinematics ideas here. And so one of the big ones would be our main, this is literally just called the kinematic. And this is going to be summing our position through all the different ways that our position can change with respect to time. And so we get a quadratic piece, which is due to acceleration. This is 1/2 at squared. We have a linear piece, which is our initial velocity times time. And then we have a constant piece, which would be any x offset here. Now, most of the time, we'll be able to cancel out some of these units. We might be in a condition where there's no acceleration in the x, or we're measuring our starting point from 0, so the offset goes away. But the full version would include every term, just in case we aren't able to cancel these out. It won't get any more complicated than this one can get. And so what we can do with this is we can use this to predict projectile behavior. Now this is going to be a big idea, very likely to show up on the exam, and that is being able to use two of these equations simultaneously. So to be specific, this is actually the x component of acceleration. This would be the y component of our acceleration. And so if we don't have any forces in the x, which for most projectiles we won't, because a lot of times we'll be ignoring air resistance, then there won't be any acceleration in the x. But we'll usually have an acceleration in the y. Most common acceleration in the y is gonna be gravity. And so most of the time we'll be able to set this acceleration in the y equal to g. Once again, g is gonna equal 9.8 meters per second squared. And if we define upwards as positive, we need to include this is going to be negative because we're going to be accelerating downwards when we are launching a projectile. And so these two functions, all they really do is you give them all these inputs and you can give them a time. And what they do, they are a function of time. You can spit in, you can put in any time into these and it will give you out the position it is at that time. And these two are paired because they will have the same time parameter. So typically for a projectile problem, we'll approach this by using the y equation to find out how long we were in the air. That would be setting this side equal to 0, because that would be the time that y equals 0 is the time that we landed. And then we can solve that for t to find the time that we hit the ground. And once we have that time, we can use that in our x equation to find out how far we traveled in that time. That would be a way to calculate something like the range. Cool. Yeah, and again, most of the time we'll be able to cancel terms out of this kinematic, but if you're ever in a really kind of messy situation where you can't cancel any of them and you're not sure how to solve things down, you can always use the quadratic formula. Now that's kind of a worst case scenario because it's a little bit messy. Ideally, we want to cancel things away, but you can always just go with okay, let's do this as a t. But so t is going to equal, we have x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And so this is for the format of a quadratic. I used t instead of x, but something where these a's, b's, and c's are just coefficients to each term. And so in this case, a would be 1/2 ay or 1/2 ax. B would be vy or vx. And then c would be the x offset or the y offset. Oh, thank you, Morty. I appreciate that. Yeah. And I think that's more or less. Oh, there's one more kinematic equation worth mentioning, which is going to be our Vf squared is equal to Vi squared plus 2AD. Now, what's nice about this one is this is time independent. We're able to work out information about our final velocity, or our distance traveled, or our acceleration without having to get a time parameter in here. Now, but this one is it's a little bit tricky because it actually comes from conservation of energy. But we'll get into that a bit more once we get to the work power energy. Do we want to do an example? Sure, we can do. Let's do a quick example. Let's see. So let's say I wanted to find out. Let's get a new page here because we're gonna run out of space otherwise. So let's say I wanted to go cliff jumping, and there is a nice cliff jump of some height h. I guess let's say that's gonna be let's say that's 20 meters. And so the catch to this is that there's rocks on the ground before I hit the water. So if I'm up at the top here and I'm gonna try run off to the side without jumping, just horizontal velocity, what velocity do I need to achieve to clear this distance? I guess let's say that's, let's go with 5 meters in order to reach the water safely without landing on the rocks and hurting myself. So in order to do this, we're going to use our paired projectile equations. We're going to start with our y expression, which is going to be 1/2. Our acceleration in the y is g, so I'm just going to plug in g right away. Our initial velocity in the y is going to be 0, so this term cancels out. And then we're going to start at a height of 20 meters. And and we want to make sure that g is going to be a negative, so we'll put a negative sign in there. Yeah, and then in my x direction, I have no acceleration in the x, so this term goes to 0. I have my initial velocity in the x is the velocity that I am running because I'm just going horizontally off the side. And we're going to measure from this distance there, so there'll be no offset. So that term's going to go away also. So we can start with our y equation up here, looking for the time it takes for us to reach y equals 0. So we'll set 0 is equal to negative 1/2 gt squared plus 20 meters. Now I want to solve this for t. I'm going to bring the negative term over to the right, giving us 1/2 gt squared is equal to 20 meters. We want to get t on its own, so we'll multiply by 2, divide by g, and take the square root, giving us 20 times, what do we have, times 2 divided by g, and then all under a square root. So that's going to be 40 divided by 9.8, and I need to use a calculator for that. And I don't want my phone to start making a bunch of noise. So let's go 40 divided by 9.8 to the 1/2 power. Cool. And so I get a time of 2.02 seconds. So that's the time that I'm going to be in the air. So I need to make sure within this 2 seconds, I'm able to clear a horizontal distance of at least 5 meters. And so I need the minimum velocity I can have would be, on having issues about making acceleration positive or negative, the key for that is thinking about the direction of your motion. Typically, we'll want to, so you're able to define your coordinates however you like, but it's going to be best for us if we define them in the direction that we are moving. And so if we have if we're moving horizontally, we'll have that be a positive. Moving to the right would be a positive, and then moving to the left then would be negative. We expressed our height as a positive value, so that's an upwards height. And so then that would mean moving downwards, acceleration due to gravity, we treat as a negative. That's why we brought this negative here. To be honest, there will be cases where sometimes you drop a negative somewhere and it gets a little bit confusing, but as long as you can keep your directions straight about everything it's moving around, you can usually get away with just using the magnitude. But I wouldn't recommend that on an FRQ because they could dock you points for that. So we have this time here now, and we want to use this in this x equation. And we want the condition for our minimum velocity that we need to travel 5 meters while traveling at some velocity v, and for a period of time t. And we know that period of time now is now going to be 2.02 seconds. So to solve for v, we just divide both sides by 2.02. That's going to be 5 over 2.02. It's meters per second, so we have units of meters per second. That's units of velocity. And that's going to be about 2.5, 2.47, 48 if we round. So I need to achieve a speed of at least 2.48 meters per second if I'm going to safely clear these rocks and land safely in the water below. Yeah, any questions on how we set that up? Alrighty. Well, I think that's about all I have to say on kinematics. Now, this will still follow us around because one of the beauties of physics is it does keep building on itself. But then that's kind of an issue if you struggle with some of the foundational things, is that they aren't gonna just kind of disappear. They will show up again. But so next we have dynamics. And pretty much all of dynamics can be summed up with one major equation. That's going to be this guy, Newton's second law. This tells us that our net force acting on an object is going to be equal to its mass times its acceleration. Now, typically what we want to do for these types of problems, whenever we have an object, is we'll draw a free body diagram for that, which means we get a little picture to represent it, and we draw arrows to represent every force that's acting on it. So let's say I have some box that I'm pulling along on a surface with some friction to it. And so the free body diagram, I would have a force of tension pulling this way. I would have a force of friction pulling backwards. I'd have a gravity force pulling me downwards. And then I'd have a normal force from the surface pushing me upwards. And so I would label these. So I like the notation where we label everything with an F and then a subscript. Although I've seen notations where you just use the subscript. So tension would turn into just T. I personally prefer using F of T, but both are acceptable. It's just so you will find cases then later on where something like T might mean something like period or maybe torque. And if you have lots of T's showing up all at once, you want to make it very clear which one you're referring to. And so sometimes just using the F sub T is a little bit cleaner. And this would be Fn for our normal, and then this is our friction force there. And so we can find our acceleration in each direction by looking at our net forces. Now we want to split this up by direction. And so if we define our coordinates in this case to be x moving that way and y moving this way, we write our net forces by adding the positive forces pointing in the direction of our positive direction and subtracting our negative forces. So for the y, we would have a positive Fn minus an Fg is going to equal our mass times acceleration in the y. And then for our x direction, we would have a positive Ft, because that's pulling to the right, minus our Ff, which is going to be pulling to the left. And a friction force is always going to be pulling in the opposite direction of motion. Unless it's static, and then it's going to be pulling in the opposite direction that it would want to accelerate without friction. And so this is going to equal our mass times our acceleration in the x. Now, if we know conditions like if we're told this is a constant speed, or we're told something that like it's at equilibrium, is another kind of keyword, if I can spell equilibrium. There we go. Or static equilibrium is another one. That tells us that our acceleration is going to go to 0. And if our acceleration goes to 0, that tells us that our forces have to be balanced. I guess, yeah, balance is another kind of keyword that might show up. So in this case, most of the time for an object moving across the ground, we expect the acceleration in the y to be 0. And that would tell us that our Fn is equal to our Fg. And then if this is moving at a constant speed, that would tell us, so the operation that I'm doing here is I'm setting the right side equal to 0, and then I can add the negative thing over to the 0 side. So that would be Ft, and I add the negative Ff over to both sides, giving us a positive Ff over here. Yeah, and so that's going to be very useful for equilibrium types of problems. If we are not at equilibrium, we do not expect the acceleration to go to 0. And in that case, to solve for the acceleration, we need to find other ways of expressing these forces. The friction force we'll often see is going to be expressed using what's called a coefficient of friction. This is going to be our little mu here. And it's going to be mu times our normal force. So most of the time, if we're on a flat surface, our normal force is going to equal our gravity force. However, there will be cases when this is not the case. And that would be if we have any upwards forces helping us out, like say maybe our tension force is going up this way, so we're kind of taking a little bit of pressure off of the surface, or if we're doing something like, say, an inclined plane, where the normal force is going to be acting perpendicularly. And so an inclined plane is a type of problem we can expect to see. And for this type of problem, we want to remember to set our coordinates in the direction of our motion, which is going to be parallel with the plane. So we treat our xy as something like this. See how we're rotating it to line up with our angle here. A lot of times we'll be given the angle of the plane as an angle theta there. And so for our block on the plane, we would still have all of our usual forces. We'd have gravity pointing downwards, but now our normal force, the word normal in normal force means perpendicular. So this is going to be perpendicular to the plane, and so it's going off at this angle, and it's no longer going to completely balance with gravity. And then if we have friction, that would go up this way, because we'd want to be moving down the slope. And so what we can do is, because we have our coordinate system lined up this way, our force of our normal force and our friction force are going to be aligned with our coordinate grid, but our gravity force no longer is. So we have to break gravity into components. Again, going tail to tip while following the directions of our coordinate system. So I'm going to go down the y, and then I'm going to go over in the x. It's like following city blocks, right? Trying to find, say a crow is flying over the diagonal of a city block. I can either go over one block and then up to go meet it, or I can go up first and then over afterwards. And so an equally valid way I could have broken this into components would be going left first and then coming down afterwards. I'm still going tail to tip and reaching the end here. And then you can actually see, this might be a fun activity to prove on your own, that these are going to be congruent triangles. And this angle theta is going to be the same angle as our incline. So we'll be able to relate our force of gravity, which is our hypotenuse, to the y component and the x component of our gravity, which are then going to be acting in these y and x directions. And that's what we can use for our Newton's second law equations. So in this case, so this would be like our fgx, and this would be our fgy. If this were, say, in static equilibrium, that would tell us our acceleration would equal 0. And so we would have let's start with the y direction. Our positive y direction, we have a positive Fn, and then moving down, we have a negative Fgy. And then in the horizontal direction, or the x direction, so kind of the angled down horizontal direction, we would have a positive Fgx, and then pulling back up the hill is force of friction, Ff, which we subtract out. And so these are both equal to our mass times our acceleration, acceleration in the y and acceleration in the x respectively, but we expect these accelerations to be 0 if we're in equilibrium. So these terms drop out. We can add the negative terms to the other side, giving us that our Fn is going to equal our Fgy, and our Fgx is going to equal our force of friction, Ff. Now we can get this Fgy and Fgx in terms that we can work with better using our trigonometry. So I'm going to take this little red triangle we've got down here, and I'm going to draw it again at the bottom here, but I'm going to set it on its side here, so it's a little bit easier to work with. And so we have the y component and the x component. And so we know this is our hypotenuse. This is Fg, which is just going to equal mass times gravity, times the acceleration due to gravity, which is g. We have our Fgy, which is what we have up here. And we have our Fgx. And we know the top angle is theta. So if I wanted to find Fgx, well, this is opposite to my angle theta. So it's going to relate to the hypotenuse with the sine relation, which tells us the sine of theta. Sine would be the SO in SOHCAHTOA, that's OH. So opposite over hypotenuse, in this case, is Fgx over Fg. And so if I wanted to get Fgx on its own, I'd multiply both sides by Fg, giving us Fgx is equal to Fg times the sine of theta. And this was really mg, right? So this, if we knew the mass, this is now something we can calculate. And we can do a similar thing with Fgy, only in the case of Fgy, this is adjacent, so we'll use the cosine relation. And so the cosine of Fgy, or the cosine of theta is adjacent over hypotenuse. That's the ka in SOHCAHTOA, which is going to be Fgy over Fg. And then once again, to get Fgy, we multiply both sides by Fg. And that gives us Fgy. So we've got, what's the difference between the coefficient of kinetic and static friction? No, kinetic has to do with motion, but how do we calculate and use the two? Are they both solved by force of friction? Yeah, so that's a good question. And the short answer, it's exactly that. Kinetic is going to be when we are moving. So that it would be like a mu sub k. And so that would be for a case when we do not expect acceleration to equal 0. If we have a static, that means that we are at rest. Now, typically, just a general rule of thumb, we expect static coefficients of friction to be higher than their kinetic counterparts, which means that a friction force will have a stronger magnitude if it stays at rest. But once it starts moving, the friction force will be a little bit weaker. And again, for both, they still use this same relation here. The force of friction is equal to mu times the normal force. And so in this case, we could actually find what our normal force, or what our coefficient of friction would be. If we say we have this block being held at rest, that would mean it's a static coefficient of friction. And we expect the static coefficient of friction from this relation to equal the force of friction divided by the normal force. Then we'll put a little subscript s just so we know it's static. And from these relations, from our Newton's second law, we know that our normal force is going to equal the y component of our gravity, Fgy, And the frictional force is going to equal the x component of our gravity. That's going to be Fgx. And we just calculated both of these using our trigonometry. And so that's going to be Fg sine theta and Fg cosine theta. But I'm going to plug in the definition of Fg for each here. Is mg sine theta over mg cosine theta. And so we have the same mg on the top and the bottom, which means we can cancel it out. And so we're left with sine of theta divided by cosine of theta, which some of you might recognize as a trig identity, because that's just going to be the tangent of theta. Cool, cool. I think that's more or less all we need for dynamics. Oh, I guess we should talk about pulleys too. Let's get us a new page though, because we're kind of running out of space here. Now for pulleys or an Atwood machine, we have some sort of, so in the massless frictionless case, if not, we have to deal with torque, which we'll talk about when we get to the torque section. But we have basically some objects being pulled by a shared rope, right? And so an Atwood machine would be just two masses hanging on either side, but you might have a case where on one end, instead of a mass, it's like someone pulling with a force. But either way, we expect these to have a shared tension. So let's say if we have these, let's label these as M1 and M2, and just for sake of argument, let's say M1 is going to be greater than M2. So generally, we expect the pulley to rotate this way. So that's going to be an acceleration downwards for M1 and an acceleration upwards for M2. So for each of these separate masses, we want to define that respective direction as the positive value. That means for M1, the downwards direction will be positive, and for M2, the upwards direction will be positive. And so we can use our Newton's second law. We'll start with a free body diagram. We have a tension force pulling us upwards and a gravity force pulling us down. And notice how I'm drawing the gravity force larger than the tension force, because we expect this to overpower the tension force and accelerate us downwards. And then similarly with M2, we expect an upwards tension and a downwards gravity. And then vice versa, this now is the larger one because that's going to be accelerating us upwards. Now, due to Newton's third law, we expect the tension force between these two to be equal for both. That is only satisfied under the condition that this is a massless pulley, but that's pretty much what we're going to see for most of our problems here. If not, then we'll see it with torque. And so for each of these, we have a separate Newton's second law equation, which we can then combine. So for M1, we have downwards is positive, so that's going to be an Fg1. So yeah, we'll start labeling it like that. Minus an Ft, which is pointing upwards, is going to equal my mass 1 times acceleration. Now notice how I didn't do mass 1 plus mass 2. This is just the forces affecting mass 1. And then for the second one, we have upwards as the positive direction. So we get a positive Ft minus our Fg2, which is just going to be our second mass times the acceleration due to gravity. And this is going to equal m2 times our acceleration. So again, we're only looking at m2. But because these are bound together, we expect Ft's to be equal, and we expect our acceleration to be equal. And so that means we can use these two equations to substitute into each other to find information about our acceleration. So let's start. I like the look of this m2 equation because Ft is already kind of on its own and positive. All you need to do is move Fg2 to the other side. So we get Ft is equal to m2a plus Fg2. And I'm going to invoke the definition of Fg2 as m2g. And so now we can take this equation and bring it over to these guys on this side. And so I can rewrite this first equation. Let's invoke the definition of Fg1. And then we're going to minus an Ft, which is going to be what we found on the right side. That's going to be m2a plus m2g. It's going to equal m1a. Now we can distribute this negative through, giving us m1g minus m2a minus m2g is equal to m1a. Now we want to get acceleration on its own. It's the only unknown we have here. So we'll bring this term over to the right side and then factor out our acceleration. So we'll have m1g minus m2g is going to equal m1a plus m2a. And so we can factor these out. On the left side, we have a g in both terms, so we can write this as g times m1 minus m2. And on the right side, we have an a in both terms, so that'd be a times m1 plus m2. And then to get a on its own, we just divide by the sum of the masses here, giving us our acceleration is going to equal g times m1 minus m2 over m1 plus m2. So the key takeaways from this type of, and so this, by the way, this you might recognize is the Atwood equation. And so this is going to be for a pulley system or an Atwood machine of this type of quantity. Will always look something like this. But so the key takeaways we had to use here is we had to split up our coordinates. So we had different coordinates for each block. We had to only use the mass for the individual block on the Newton's second law. And we expected our accelerations to be the same and our force of tensions to be the same. So that let us use two equations to substitute into each other to solve for two unknowns. And I think that's more or less all we have for dynamics. Again, it's going to show up later, but we'll see how these dynamic ideas play out more. And so next, we have centripetal motion. And so this is going to play very similarly to dynamics. It follows a lot of the same rules, only now we're looking at forces that can induce an object to move in a circle. So if we take a circle here, and we think about, so an object's like moving around in a circle. Let's say we have, I don't know, let's say it's like a block kind of hanging on the end of a string, right? And we're moving around this way. This block will have some tangential velocity. And so this means it's moving at a velocity that is tangent to the edge of the circle, which means that it is only touching it at one point and then moving away. And so it's just moving around the edge. And we can relate this tangential velocity to the net force pointing radially inwards. And that's going to be our centripetal force. And so we define our centripetal force as mv squared over r. Now, another way we can look at this is we define our centripetal acceleration as v squared over r, where r is our radius from our radial distance from the axis of equation, from the axis of rotation. Yeah, there is an Atwood equation for pulleys. I don't know since when. I assume probably a while because pulleys are fairly old technology now, but quite exciting. And so this, if we use this as centripetal acceleration, we can really just write this as Newton's second law again. It's our net force in the centripetal direction is equal to our mass times our centripetal acceleration. Now, we kind of threw out a little term there without thinking too much about it, was in the centripetal direction, which kind of, what does that really mean? So our centripetal forces are going to be the net forces that are pointing radially inward. So we're looking for forces pointing radially inward to be positive. If we have a force that's on the same axis but pointing radially outwards, we have to subtract it from our centripetal force. And so using these sums, we're able to compare these to information about the velocity that we're moving around a circle, or maybe the radius of the circle itself. If we say we need to maintain a specific velocity with only a certain amount of force at hand, Or we could do this backwards using information from our velocity and our radius to deduce information about the forces necessary. All would be using this relation and just kind of rearranging it for whatever value we're looking for. Now we have a couple more pieces we can use. That would be to relate velocity to the period. Now the period is going to be the time it takes for our object to complete a single lap. And so we can think about our velocity we considered as distance over time, or displacement over time, technically. And displacement over time, in this case, would be we travel an entire circumference every period, because a period is the time it takes to complete one lap, and one lap around a circle, if we travel around the edge, is a distance of a circumference, or 2 pi r. And so the distance over time would be 2 pi r over t. Now this is how we can relate velocity to the time it takes us to complete a lap. And we can take this entire relation and plug it into our FC like this, writing our FC as m times 2 pi r over t squared, again divided by our radius. And we can rearrange this relation to solve for information about the period of our velocity, or use information about the period of our velocity to solve for information about our forces. Any questions on that so far? I think that's more or less. Oh, also included in this unit is gravitation. And so they kind of tack this on the end here because this is a really good unit to talk about it, because when we're in space and orbiting using large-scale gravity, our gravity is the only force pointing radially inwards. So it is the de facto centripetal force. And so usually, for most of our cases when we're near Earth, we can write Fg as mass times gravity. But this doesn't really capture all the nuance of what's going on when we start getting to larger distances or much higher speeds. And so in order to account for this, we need to use a more robust definition of gravity. And so that's going to be using what we call big G gravity. We have this big G, which is a constant, times the mass of the object we're orbiting, times our mass, the mass of the object that is orbiting, divided by the radius between them squared. And so this is going to be our force of gravity. Notice how it depends on the mass, and it drops off by the square of the radius. So as you get further away, if we double the distance we are away, we reduce the size of our gravitational force by a quarter, to a quarter. So we reduce it by 3/4. Yeah, and so because when we're in space and in orbit, this is the only force pointing radially inwards, we can write this as mv squared over r. Again, that would be the same r, like our nice big R. And so this gives us information about our orbital velocity. And if we use the version with 2 pi, again using the big R, over t squared over r, this gives us information about our orbital period, which is also something we'd be interested in solving. And I guess one more thing, we'll mention this a bit more with work and energy, but our potential energy for gravity we usually write as mgh, but when we're on the larger scale, we want to think of this, because we can think of this as fg times some distance that we're traveling, right? And usually that's a vertical distance, so we use h for height. But on the larger scale, it's going to be a radius r. And so on the large scale, our gravitational potential is going to equal our gravitational force, so this big guy, times a distance r. And so that's going to cancel out with one of the r's on the bottom, giving us just gmm over r of our two different masses. Yeah, I think that's more or less everything that shows up in this unit. Any questions on anything so far? Cool. Good stuff. I'm going to grab a quick drink real quick. But next we'll be taking a look at work, power, and energy. So statistically, this is the largest unit that's going to show up on the test. The bulk of Well, uh, this has the plurality of the questions, as in there are more questions about this than any other unit, but this isn't the majority of questions. This isn't going to be over half of the questions. It's going to make anywhere from 24 to 28% of the test, which is the biggest chunk of any individual unit, though, considering we're splitting this across 7 units. And so the big idea for this unit is that we have a conservation of energy. And so we express this as our final energy is going to equal our initial energy. Now this is for a closed system, which means we don't have any outside forces adding energy or taking energy away. If we have an open system, we have to take into account those outside forces and think about how they're changing our energy. And to do that, we have the same equation, but then we add in a term for work on the end. Now work we can define as force times distance times the cosine of the angle between them. I guess this is technically d for displacement then, because that would be a vector quantity. And so if the force is pulling parallel to the distance, to the displacement, excuse me, this cosine goes to 1 because the theta goes to 0. If it's perpendicular, the cosine goes to 0, and then the work done goes to 0. I'm going to uncancel that, though, just so we can see this relation nice and clean here. And so this gives us then a way we can think about this equation is telling us that the final amount of energy in our system is just going to be the energy that we started with plus the energy that we put in with an outside force. We can also define work on its own by subtracting EI from both sides, giving us EF minus EI is equal to work, and that's going to be delta E, the change in energy. So we might not be able to calculate the work because we might not be given information about the force or the displacement, but we will be able to find differences in energy based on changes in potential or kinetic energy, and whatever energy is not conserved is changed by that outside work. And that then gives us information that we can use to solve about the force or the distance. And so our energy we can split into 2 main types here. That's going to be kinetic and potential. And potential we usually write with a U. Now there are a few more types of energies we'll see, specifically thermal and chemical, but they're not going to show up at this level. But you might, worth keeping in mind just in case for, in the experimental type data when we're thinking about, oh, these don't line up perfectly. Well, yeah, some of the energy might have been lost to heat. So it's worth keeping those in mind. Our kinetic energy we define as 1/2 mv squared. Our potential energy we define differently based on what's providing that energy. But for gravity, we write this as mgh, or the big G one that we saw before, but that's very uncommon, or at least at this level, very uncommon. And we'll also see spring potential. This is the potential energy of a coiled spring being held together. That's going to be 1/2 kx squared. Yeah, I think that's the only types of potential we see. Is there? Oh, there's another type of kinetic, but we'll talk about that when we get to rotational. But I guess so we can see it now. The other type of kinetic energy, the rotational, is 1/2 I omega squared, where I is our moment of inertia and omega is our angular velocity. But we'll talk about that a little bit more once we get to angular velocity. So we use these conservation of energies to find our to solve for information about our velocities or our distances a spring might be compressed, or a height that we travel down or up based on just changes in our energy. And so the full version we can write this equation into would be summing our final kinetic energies and potential energies and setting them equal to our initial kinetic energies and initial potential energies. So 5 terms is kind of a pain, but usually we'll look for situations where we can eliminate some of these terms. We might be interested, say, in starting at where all of our energy is in potential, so our initial kinetic goes to 0, and then measuring the total amount of velocity we have at the end after all of our energy goes into kinetic. So that term drops out. And then whether or not we have work would be whether or not our system would be open or closed. Yeah. And so I think that's more or less it for energy. Oh, and power. We need to talk about power. And so power is then going to be adding these same conditions of energy, but now we're introducing a time factor. And so we define power as work over time, but technically we write this as a delta t, because this is just the change in time or the period of time at which we are doing the work. And that's then going to be equal to our, we can write this as our change in energy over the change in time. And so this is going to be units of watts or joules per second. Yeah, energy is going to be in joules, which is newtons times meters. And power is going to be in units of watts, which is going to be units of joules per second. Or current times voltage, but again, we're not going to be dealing with that at this time here. But yeah, there's a lot of nice ways we can move between these units, which is useful. But yeah, more or less, this is how we set up most of our energy type problems. If you want to see some more specifics, go ahead and check out our previous streams at 3on4education.com. We have one just about work, power, energy, where we're looking at different cases, all different practice problems. We get into all the different strategies there. But these are going to be the broad strokes of just kind of the big ideas that we can expect to see from this unit, and what kind of ways we might be expected to manipulate these equations to get to solve for our answers. And so next we have momentum and impulse. And so momentum is going to be another conservation law. So again, this follows, we use P for momentum, and we expect our final to equal our initial for a closed system again. And then for an open system, that means we have something else performing an outside force to us. That's going to introduce what we call an impulse term, which we have as a plus J. And so, well, so let's define our momentum first here. This is going to be our mass times velocity. And if we want to get really picky about it, it's actually going to be the sum of our masses times velocities. So this is just using a summation notation where we have this little I counts up to n, where n would be the number of masses moving that we have. So if we have two masses coming towards each other and they both have a velocity, they both contribute momentum to the system, and we have to add both of those together. So that would look something like m1v1 plus m2v2. And that we could then say their initial momenta are going to equal their final momenta. This does not mean that they have to have the same velocities as before. We just expect the sum of the product of each of these to be the same. But we can find ways where we might be able to manipulate this in cases where the velocities will not be equal. And so for this impulse term, back to the open system case, we have our impulse. I guess let's move this over here. Impulse we're going to define as going to be the force, or technically the average force, over the change in time that we applied that force. And so for a force time graph, that would be given as the area under the curve. So say we have a force that kind of spikes in this short period of time, but we have an amount of force given throughout this entire thing. The area under the curve is going to equal J. I'm just going to label that as AUC, like awk. Cool. Let's see. What else do we have? Impulse. Oh, yeah. And so the reason why, so we want to use momentum for collisions rather than conservation of energy. Because technically, well, if energy is conserved too, can't this do everything that momentum does, but better? Well, what momentum is useful for is for collisions. Now, there's going to be two types of collisions we're interested in. It's going to be elastic versus inelastic. And so elastic is going to be the case where we have two objects and they bounce off of each other perfectly and then keep moving right afterwards. And the condition we expect for that would be that our kinetic energy is conserved. That means that our final kinetic energy of our system is going to equal the initial kinetic energy of our system. Whereas now we look at inelastic, and that's going to be the case where we have two objects that hit each other but then stick together or move together in some sort of way. And so this so again, these are also kind of ideals, right? We have ideally elastic and ideally inelastic, but a lot of collisions might end up kind of somewhere between these two. But in the inelastic case, we do not expect kinetic energy to be conserved. Kinetic energy is not conserved. And so we can't use conservation of energy for inelastic collisions. For that, we need to use conservation of momentum. And so something like that would look like if we have some object of mass, let's call it m1, hits a larger object of mass m2, and m1 is traveling with some initial velocity, I guess we'll call that v1, and then afterwards they move together as a single object moving to the right with some v final. We can calculate that v final with conservation of momentum. So that would be our initial momentum. Our mass 1 is the only thing moving in the first case. So we have m1 times v1. But then afterwards, we have as one whole mass m1 plus m2. So we're going to combine these masses like this and say this combined mass is traveling at a v final. And to find out what that v final is, we just divide both sides by this m1 plus m2. It's going to be m1 v1 over m1 plus m2. And we'll see this type of problem shows up a lot because this is something that momentum does really well that conservation of energy really struggles with. So this is a good example for momentum. Oh, and then one last one, I guess, worth mentioning. For the impulse case, again, we can use the same trick we used with work by solving for impulse from the conservation relation, giving it as pf minus pi, which means that our impulse is equal to the change in momentum. So we can then use that to get information about the average force applied from the outside or the time that it was applied based on comparing our initial momentum to our final momentum. Maybe we're given information about our different velocities and we can calculate each momentum by hand. Any questions so far? All right, cool. We're making great progress here. We've got 3 more left, 2 more left. This is the second to last one, I believe. And so next we have simple harmonic motion. Now statistically, this is going to be the smallest unit on the test. And that's because this is a very difficult concept to describe without using calculus. But typically, we're going to be thinking about some sort of object that is moving back and forth between set states due to some sort of restoring force. So a nice example we like to use is a mass on a spring. So if we have some spring with constant k and a mass with a mass m, and this spring is going to go back and forth, we expect our spring force to be proportional to the opposite of our displacement times k, right? X is how far we move from our equilibrium position. And so the further we move away from the equilibrium position, the stronger the force is to pull us back. And so we'll get these cases where we then accelerate towards the middle very fast, but then once we reach the equilibrium, we have so much velocity that we go right past it. And then we compress the spring, which then creates a stronger force pointing again in the opposite direction. So in this case, that would be pointing to the right. And then that points our force to send us back to the equilibrium position again. Again, restoring us back to that original position. And so this type of motion we call periodic. And so that means there's a period that it has to oscillate between these states before it returns to that initial position. And so we describe this type of motion with a sine function. And so we can write this as the amplitude, which is going to be the maximum distance that we displace from the center. For mass on a spring, that's just going to be the literal distance. For a pendulum, that's going to be sort of the starting angle that you lift it up to. Because, yeah, pendulum's another simple harmonic system. And then we use either a sine or a cosine. Technically, either will do. And then we multiply this by, or we put in the argument of the sine, an omega, which is an angular frequency, which also shows up in circular motion, times our time. And then we can include this term for a phase angle if we want to offset this. And what's good about this phase angle is that means if we chose sine in a case where cosine might have been more prudent, we can just adjust this with this phase angle to shift our graph over by pi over 2, ostensibly making the sine into a cosine, or vice versa. The reason we'd want to choose one or the other would be due to initial conditions. We want to see whether or not at time t equals 0, we want to begin at position 0 or at position A. And that will tell us whether or not we want to either choose sine or cosine or to fill in something for our phase angle. Now, this omega is our angular frequency, and so that means that we complete a cycle every period t. And the cycle for a sine, we can think about if we picture the unit circle, sine repeats itself once we come around a full circle, which is 2 pi radians. And then the frequency would be the time it takes to do that, or we want to relate this to the time it takes to do that, so we divide that by t, again the period, just like we saw in centripetal motion. And in this case, for simple harmonic motion, we can express these omegas with our physical systems. For a mass on a spring, that's going to be the square root of k over m. And for a pendulum, that's going to be the square root of g over L, where L is the length of our pendulum. Now, these are the only two simple harmonic systems that we'll see on the test. There are technically more, but for now, these are the only ones we need to keep track of. And so notice how our mass on the spring system, the period, so this, because we can set this still equal to our 2 pi over t, so we can directly compare our k value and our m value to the period of oscillation. And so we see this depends on the mass. If we increase the mass, then that changes our period. But that we can see for our pendulum case, which again we can set equal to 2 pi over t, that this does not depend on the mass. So if we increase the mass of the bob on the end here, that doesn't actually change the rate at which we're oscillating. And so the pendulum only depends on the acceleration due to gravity, which hypothetically could change. I've seen a couple problems where they take you to some new hypothetical planet where g is now reduced, or we change it with the length of the pendulum. By increasing the length, we decrease the period. Cool. I think that's more or less all. Oh, I guess another thing we should probably note is we can use our conservation of energy very well here. So if we look at our mass on a spring example, because this is kind of the version they are more likely to ask about, we can compare at its maximum displacement, all of our energy is going to be in potential, because at the maximum distance of stretching, that's when we're changing directions. So that's when our velocity crosses zero. And so when we have all potential, that's going to be spring potential, which is 1/2 kx squared. But I'm going to plug in for x our amplitude, a. So we'll have this as 1/2 ka squared. And then when we go through the middle, we're going through the center, our x goes to 0. So the potential due to the spring disappears. And so all of the energy in our system is going to be in kinetic. And that's at the equilibrium position, is the time of max kinetic energy. At the far ends are when we are at our time of max potential energy. And so we can use this relation to directly compare information about our spring constant, our mass, and our amplitude to our maximum velocity. If we wanted to find our velocity, it's quite simple. We'd divide both sides by 1/2, divide both sides by m, so we get k over m times a squared is equal to v squared, and then we take the square root of both sides. So we get the square root of k over m times the square root of a squared. Those are under the same square root, but I just split it up because they commute. And then what's going to be nice about this is this can, that's also squared under square root, excuse me. And so what we can do then is we can write this as a times the square root of k over m, which is going to be v. And so what's kind of neat is we see that this is a times omega is our v. That's our maximum velocity is going to be our omega value times our maximum amplitude. And yeah, that's more or less all we're going to really see for simple harmonic motion. They might ask you to, so this equation will be provided on the test, maybe with a cosine instead, but it's the same relation. And they might ask you to fill in a couple conditions. So they might say, if they give you like an amplitude and the spring mass and all that, they might ask you to write a version of this where you plug in values for a, omega, and phi. But generally, I'd expect them to be just talking generally about maybe comparing how we can change these factors and how that changes our period, or looking at maybe velocity compared to our offsets, to our full displacements or our highest angles for our pendulum. But yeah, typically we expect this to have the least amount of representation on the test. So so I would, if there's one unit that you really don't have time for, this is probably the one that you could drop. But I mean, it's worth checking out. I mean, especially if you plan on doing physics later in college, because this is a really special idea that is really helpful in describing a lot of very complicated systems. And then for our last unit, it's going to be torque and rotational. Now this technically has the most new equations for it, but really we'll see how these are really just all of our original equations sort of translated. And so we want to start by finding an allegory. Okay, so let's start with a circle here first. And so we have, say we measure the bottom of this to kind of go down here, and then we're going to rotate this circle. We're going to rotate it by some angle theta. Now I want to relate this angle theta to the distance around the edge. Oops, if I can draw curved side here. I want to relate this to this length here, which we call the arc length. I'm going to label that as an S. And now I can think of these in terms of fractions. So my fraction for theta takes up some portion of this circle. We can think of it as taking like a slice of pizza out. And what percentage of that did it take, or what fraction did it take? Well, it took theta 1 part per whole, which is theta over 2 pi. Theta radian, total amount. And now we expect this fraction to be equal to the fraction of our s that we took out. Now this s takes a section out from the circumference, and so the ratio would be s over our total circumference, which is 2 pi r. Again, if this is a circle of radius r. And so we can multiply both sides by 2 pi, And that gives us that theta is equal to s over r. Next, we want to think about our velocity as if we have some point moving this distance s in a certain amount of time. And we can think about how we defined velocity before. We previously said that v was going to equal 2 pi r over t, which is going to be our tangential velocity. We travel an entire circumference in one period. That's the capital T. And we want to compare this to an angular velocity. And to look for our angular velocity, this is actually going to be the same trick we used in simple harmonic motion. That's going to be using our omega, because our omega we defined as 2 pi over t, which looks really similar. The only difference is this one has an r in it. So if we divide the r out from the velocity, we get our omega. So that leaves us with omega is equal to v over r. And then to follow this trend, if we then, can I move that actually? I can't really move that. I'm actually going to rewrite these because I like to have them all three in a line. We'll have our theta equation. We have our omega equation, which is v over r. And then we have the next one would be alpha. And so this is our acceleration over r. But this is our acceleration in the tangential direction as we are increasing, excuse me, as we are increasing the rate of our rotation. And so these three ideas, this is our angle, this is our angular velocity, this is our angular acceleration. These three relate using kinematics. So we can use our old kinematics equations by just plugging in our angular quantities for their respective linear quantities. And so something like our x of t equals 1/2 at squared plus v initial t plus x initial. This equation becomes theta of t is equal to 1/2 alpha t squared plus omega initial t plus theta initial. Just finding each appropriate linear term and replacing it with the corresponding angular term. And so that's going to be kind of the big idea for our rotational motion, is finding these angular translations. And so the allegory or the translation, so this is for our kinematics. The one for force would be torque. We can think about force being the allegory for torque, which we define as the force times the radius, times the sine of our angle theta. Now, some of you might know this as the cross product, but that basically just tells us we multiply the magnitudes and then expect them to be perpendicular. And so that's what this sine of theta does. So if these are perpendicular, we get sine of 90 degrees, which is 1, which is our maximum torque. But if they're parallel, we get sine of 0 degrees, which is 0, which induces no torque. And so then we have from, I guess our other thing we want to translate is we want the equivalent of mass, which we want to think of mass as not going to be measuring the amount of matter, but measuring an object's resistance to changing its motion. If we think about how we had A was equal to F over m from Newton's second law rearranged, the larger this mass gets, the more force it takes to get a significant acceleration. So the more mass we have, the more inertia we have. And so the more resistant this object is to change. And so this mass we want to think of as a moment of inertia. That's going to be this I, which is going to include a mass term, but it's also going to include a radius squared term. And so this r squared kind of tells us about the distribution of mass. And so the further the mass is distributed away from the axis of rotation, the higher the moment of inertia, the more resistant our object is to changes in its rotational motion. So it's resistant to changes in rotation. And then we often have different cases based on the object for our coefficient here. This could be a 1/2 for a cylinder. For a point-like mass, it's just mr. And then there are different cases, like maybe you're oscillating around a rod. And we also, what we can do with this is we can add them linearly. So my total moment of inertia of a system, say I have a disk and a rod, and I wanted to rotate this system. My moment of inertia total would just be the moment of inertia of the disk plus the moment of inertia of the rod. We can just add these together like that, which is nice and convenient when we're dealing with more complex systems. So now that we've got these translations in place, we can actually reuse our old equations. So similarly to how we had F net was equal to ma, this was Newton's second law, very important equation, we can translate this to a rotational version, which would be our net torque is equal to, instead of mass, we use I, instead of A, we use alpha. And so this is our net torque is going to induce an angular acceleration unless this is balanced. And then that would be the case where angular acceleration goes to 0. And those are going to be like our static equilibrium problems we did in the dynamics unit, excuse me. So this is our equivalent of Newton's second law. Our angular momentum, so our momentum we defined as mass times velocity. This becomes angular momentum, which is, instead of mass, we use I. Instead of velocity, we use omega. And we can also compare this to r cross p, which is p times r times the sine of theta, just like we did with torque down here. This uses that same relation there. And then for our last one, we touched on this a little bit earlier, is our kinetic energy. So our linear kinetic energy was 1/2, I guess we'll call this translational. 1/2 mv squared, and this goes down to our rotational, which would be 1/2, instead of m, we use an I, and instead of a v, we use an omega. So 1/2 I omega squared. Now, it's worth noting, though, that if we have an object that is rolling without slipping, which means as it rolls, it moves in a linear direction, that it can have both kinetic energies. We have to add them together. That means K total is equal to the translational piece plus the rotational piece. And so that's more or less all the stuff we have for torque and rotational. That was our most recent stream. If you would like to see more specifics on this, go ahead and check us out at 3 and 4 Education. We've got our most recent torque and rotational should be up by now. If not, you should be able to find it on our YouTube or Twitch, where we look at specific examples. We do that for each unit, but they're going to be on their own separate videos for each. And so, with that, that was actually the last unit that's going to be covered on this test. So, I want to thank you guys all for tuning in. I want to thank you guys all for a wonderful year, actually. It's been a blast teaching you all. For more in-depth review, please just go ahead, check us out on our website. You also find some other resources. And, over the summer, I'm going to be trying to add stuff to it that I just think is fun and interesting. So, if you guys want to check that out, keep posted. I'll keep you guys updated with cool stuff that's going on. You can follow us on Instagram. I think we have that hiding on the screen somewhere. Again, keeping updates with the site and what we're changing. And then just best of luck to all of you on your exams. Not that you're going to need it, but it's always nice to have. And until the next time then, I want you all... I guess we'll really quickly check if we have any last questions. But it looks like we've been doing pretty good. Had a lot of engagement today, which is exciting. I like it when you guys ask questions. It means I can clarify things for you. But yeah, Thank you again for tuning in. We appreciate all the support. Until the next time, you take care, keep safe, and we'll see you on the next one. Take care now.